Here's to anyone who's ever looked up. The airheads. And the space cases.
Live long and prosper.
The flight fanatics. The armchair astronauts. And the casually curious. Here's to those who know the thrust in newtons of a Pratt & Whitney J75 turbojet engine. And those who silently ask, what's keeping this thing in the air? Here's to those who can list the name, mission history, and favorite breakfast of every Mercury astronaut. And those who've ever searched for, how does a toilet work in space? Here's to the people who know a P-38 Lightning from a P-51 Mustang. And the people who thought those were the names of cars. Those captivated by the miracle of flight. And those who are just happy to make their flight. So whatever captures your curiosity.
We choose to go to the moon.
Or propels you to new heights. When it comes to the sky, there's space for all of us.
Good evening, and welcome to the third lecture in the National Air and Space Museum's 2024 Exploring Space series, sponsored by Aerojet Rocketdyne and United Launch Alliance. I am very excited about tonight's lecture. I assume that many of you, like me, turned in to watch live last fall when the OSIRIS-REx return capsule came screaming through the atmosphere, carrying precious cargo material from the asteroid Bennu. You watched the parachutes deploy and the capsule come to rest in the Utah desert, and you breathed a sigh of relief before you were overtaken by anticipation to know what was inside that capsule. You checked the news coverage in the days that followed for images of the capsule being opened in a NASA clean room, right? Right? It wasn't just me? Right. Okay. This is a story that begins almost a decade ago, in 2016, when the OSIRIS-REx spacecraft launched on its journey to the near-Earth asteroid Bennu. 2 years later, it rendezvoused with the asteroid, and then 2 years after that, it collected its sample. And then in 2023, the spacecraft jettisoned that capsule and sent it back to Earth. Our speaker tonight is Dr. Dante Lauretta. He's an expert in near-Earth asteroid formation and evolution, and as the principal investigator for the OSIRIS-REx mission, the journey to Bennu actually goes back for him to 2011, and actually I think much earlier than 2011 to 2004, 2006, right. He's a Regents Professor of Planetary Science and Cosmochemistry at the University of Arizona's Lunar and Planetary Laboratory, and the director of that university's Astrobiology Center. And tonight, Dr. Lauretta is going to tell us what scientists have learned so far from the first analysis of the Bennu samples. I know you're as eager as I am to hear what Bennu has told us about our solar system. And so without further ado, it's my pleasure to welcome Dr. Dante Lauretta to deliver this lecture, OSIRIS-REx, Revealing Secrets from the Dawn of Our Solar System. Dr. Lauretta.
Thanks, Matt. It's an honor to be here tonight to share the adventure that is OSIRIS-REx. This is a mission that's a partnership between the University of Arizona, NASA's Goddard Space Flight Center, and Lockheed Martin, with many others, including the United Launch Alliance and Aerojet Rocketdyne, who provided critical elements for our program, leading to its ultimate success. I'm going to go back to kind of the beginnings and walk you through the adventure that we had at Bennu, and then dive into what we are learning from the analyses of the return samples, which is amazing, so get ready. First, what is OSIRIS-REx? I like to say it's an awesome acronym that captures the principal scientific objectives of our program. And it's also entirely my fault. The O is really what drives my scientific curiosity. our origins. Where did we come from? Why is the Earth a habitable world with oceans and an atmosphere, and most importantly, life? We use our instruments on telescopes to study the hundreds of thousands of asteroids in our solar system, using a technique called spectroscopy, looking at the light that's reflected off the surface, heat that's emitted, to try to interpret the mineralogy. And by bringing a sample back, we get to calibrate those instruments for one asteroid and apply that knowledge to all of them. It's also a resource identification mission. Bennu is a near-Earth asteroid. It contains, as we'll see, abundant water and carbon and nitrogen, trace metals, rare metals, base metals. It could be the target of future resource extraction to further exploration, both human and robotic, of the solar system. When we also think about near-Earth asteroids, we worry about a potential natural disaster of an impact. It affects our security. And by going to Bennu, which is the most potentially hazardous asteroid in our solar system, we'll understand the details and the nuances of the forces that push it through the solar system. Information that will be critical if we ever need to mount an impact deflection mission for an object on a collision course with the Earth. And what are we after? We're after what we call the regolith. This is the loose blanket of rock and dust that covers these airless bodies, and we are an explorer. That is OSIRIS-REx. Just so we're all on the same page, here is a simplified cartoon diagram of the structure of our solar system. The sun contains most of the mass. The planets and other small bodies orbit around it. In the inner solar system, we have what we call the terrestrial planets, rocky bodies with metallic cores, thin atmospheres. As you move out, you get to the gas giants, Jupiter and Saturn, behemoths dominated by the light elements, hydrogen and helium. And farther out, the ice giant planets, Uranus and Neptune, with abundant methane, ammonia, and water. And finally, a belt of cometary bodies and dwarf planets out in the outermost solar system. When we want to understand how these objects formed, we go to the rock record. And when we go back to the oldest rocks on the Earth, we realize they have been heavily processed and modified by geology and erosion. The record of the formation of our planet is not on the surface of the Earth. We can go to the moon and push that record back a little bit farther. But if you really want to understand the materials at the dawn of the solar system, the very first solids that grew out of a protoplanetary disk, you have to go to the asteroids. And you can see most of them exist in a belt in between Mars and Jupiter. And when we first started to conceive of going to an asteroid, getting one of these precious samples from the very beginnings of the formation of our planetary system, we thought about going out to the asteroid belt. We very quickly realized that was going to be technically infeasible. It would take a long time and a lot of energy to get such a sample. Fortunately, there's a constant flux of asteroids tumbling in from that asteroid belt to near-Earth space. We call these the near-Earth asteroids. They're typically perturbed by a gravitational interaction with Jupiter or Saturn or maybe a large asteroid in the belt itself. And that changes its orbit substantially so that it starts to interact with the terrestrial planets. It can do a close flyby of Mars or the Earth or Venus. This is a dynamically unstable population. The average lifetime of a near-Earth asteroid is about 10 million years, insignificant compared to the 4.5 billion year history of our system. However, these are the most accessible objects in our neighborhood, our neighbors in space. So we decided it would be much more feasible to target one of these such objects for our mission. And we ended up choosing a very special asteroid named Bennu. You can see here a series of images. These are some of my favorite shots of the asteroid. We got these right as we were approaching Bennu at the start of our encounter in December of 2018. And I can tell you, it was quite a surprise. Bennu comes really close to the Earth. It is one of those near-Earth objects. And because of that proximity, we're able to mount a historic astronomical campaign. We use telescopes on Earth and in space to try to infer as much information about its properties as we could. And we did pretty good in many aspects. We got the size right. It's about 500 meters in diameter. That's about the size of the Empire State Building in Manhattan. The shape is also something we're able to characterize. We use the Planetary Radio Telescope at Arecibo and another one in Goldstone, California, to map the surface at about 25-meter resolution. And we could tell it had this really fascinating, what we called spherical spinning top shape. It's interesting that such a small body would have almost a near perfect spherical form. That usually happens when a planet melts and gravity and hydrostatic equilibrium is achieved, giving you the spherical shape characteristic of planets. The fact that Bennu was similar to that was a clue that maybe it's behaving somewhat like a fluid. You can see it bulges at the equator. Centrifugal forces are driving material from the poles to accumulate in the central region of the asteroid. The biggest surprise, however, was the rough and boulder-dominated terrain. The radio telescope data, in addition to giving us the size and shape of the asteroid, gave us some clues about a property called radar roughness. How does the radar beam, which had a wavelength in Goldstone of about 3.5 centimeters and in Arecibo about 12.5 centimeters, interact with the surface? It looked smooth at those wavelengths, which we interpreted to mean centimeter-sized particles dominating the surface. This was supported by thermal data from one of NASA's great observatories, the Spitzer Space Telescope. Bennu heats up and cools off very quickly, much like a sandy beach does. So we had convinced ourselves the surface was going to be smooth and sandy. Bennu Beach, we said, is where we're going to go scoop up a sample. And then we got there, and we saw that it was rough and rugged and covered in these giant boulders with no beach anywhere in sight. So we spent about 2 years surveying this asteroid, ultimately choosing a site that we nicknamed the Nightingale, and you'll see that in great detail later on in my presentation. And we successfully collected that sample on October 20th of 2020. This is an amazing spacecraft built by our colleagues at Lockheed Martin at the facility in Littleton, Colorado. And it was a real joy to see what was started out as cocktail napkin kind of concepts, to PowerPoint presentations, to detailed CAD drawings, to this fascinating vehicle that you see standing behind me there on the image on the left. And then over there on the right, you can see that it's in final phases at the Kennedy Space Center. You can see some of the historic mission logos in the background, a real sense of history as we're preparing this vehicle to launch it on its journey to outer space. We carried an amazing set of scientific instruments. You can see the different cameras there, the Polycam, which does double duty as a telescope and a microscope, the MapCam with its color filters, allowing us to resolve subtle differences in the blueness or redness of the asteroid surface, and the SAMCam. You'll see it in action when we go down to collect that sample, documenting our contact with the asteroid surface. 3 different spectrometers. The OSIRIS is our visible and infrared spectrometer. It can see the same wavelengths that we see with our eyes, and then even farther into the infrared, where heat is emitted. And then picking up where OSIRIS leaves off is OTES, the thermal emission spectrometer, which sees deep into the infrared, giving us information about the temperatures and minerals on the surface. We flew a student experiment called REXUS, an X-ray imaging spectrometer. I'm not going to talk a lot about that today because it didn't detect any X-rays from Bennu. And at first I thought maybe the students had, learned something about the challenges of spaceflight, but it turns out Bennu didn't emit X-rays, a scientific puzzle that we still haven't figured out. The only reason we knew that instrument worked was they caught a black hole merger one day off the limb of the asteroid. It's this huge X-ray emission event, and they were so excited, they're like, Dante, it works. It actually does detect X-rays. It's the asteroid that's the problem. And that's why we explore. So it was a fascinating educational experience. And then finally we have OLA, the OSIRIS-REx laser altimeter, provided by our partners at the Canadian Space Agency. Like a laser pointer, it shoots the laser beam at the asteroid. We know the speed of light. We measure how long it takes to reflect off the surface. It has a mirror that we can sweep the laser beam over the asteroid, building up rapid 3D topographic maps. So keep that in mind in my presentation when you're seeing these beautiful boulders and the rugged 3D landscapes. That's not simulated data. That's OLA characterizing the topography, overlaying the high-resolution images from the Polycam. But the mission is really about getting a sample and bringing it back to the Earth. All of those instruments are on the spacecraft to support that primary objective. And the requirement that drove the entire mission design was to return more than 60 grams, or about 2 ounces, of pristine bulk sample. And that pristine is really important. We're interested in understanding, did objects like Bennu seed the Earth with the compounds essential for life? And the central element in that investigation is carbon. The last thing we wanted to do was contaminate the sample with organic molecules or, heaven forbid, biological materials, negating our scientific investigation. So we spent a lot of time making sure that the sample collector was clean, the return capsule was clean, and the entire spacecraft was clean. We had a backup strategy. Just by contacting the asteroid's surface, we would pick up small grains of dust about 1 millimeter in size and smaller. And this is one of my favorite images. It's a very early iteration of the sample collector we call the TAGSAM, for touch and go, which you'll see as our strategy to make a brief contact with the asteroid surface sample acquisition mechanism. And what I like most about it is the material that we're testing here. This is before we were selected, when we were in initial engineering design. You can see we really thought we were going to a beach, right? There's a nice sandy bed of test regolith underneath us there. And it shows you kind of the action of TAGSAM. We're using a gas stimulation technique. When you look at the device, it kind of looks like an air filter. I like to say it would be right at home on the carburetor of a 57 Chevy. And it's basically the same technology, only there's no air on Bennu, so we had to bring our own gas. We used high-pressure nitrogen. We push that filter onto the surface, gas blows down from underneath, and like a leaf blower, just picks up all that sand, and as we'll see, gravel, and pushes it up into that filter. It was a clean, quick, efficient technology with no moving parts, something that's essential for high probability of success in spaceflight. Here you can see the TAGSAM deployed on the end of a 3-meter-long robotic arm. That's the flight unit head that's bagged up there under a constant dry nitrogen purge to keep that sample pristine. And you can see on the forearm there's some of those shiny gas bottles. We had 3 bottles of high-pressure nitrogen, allowing us 3 separate attempts to collect a sample. Full redundancy in that hardware. So that is the only part of the spacecraft that's designed to contact the asteroid surface. We were going to fly in, push the TAGSAM against the surface, blow down the gas, scoop up the sample, and then back away. So here's a concept of what we thought the sample collection maneuver was going to be like. You can see the robotic arm is extended just below the spacecraft. We have a nice flat surface with no boulders or rocks, very sandy, a nice hard surface that we touch down on. Blow that gas, spend about 5 seconds collecting the sample. A little bit of dust gets kicked up, looks nice and safe and easy. Maybe there's a little bit of boulders there on the side. And then once we verified that we had the sample, we open up a return capsule, very much like the Stardust capsule that I got to see here before the presentation. We put that filter in a custom capture ring, detach it from the arm, close up that capsule, and get ready for the journey home. Here is our timeline. One of the things I'm really proud of on the mission is the effort we put into our graphic art to kind of tell our story. You might notice my little lapel pin. Here's the parachute. This was the 2023 pin. We released one every year to accompany these commemorative posters. You can see we launched in September of 2016. At that point, I'd been working on the project for about 12 years. We started in 2004 with proposals, and finally win in 2011. We spent the 5 years designing, building, testing, and preparing this spacecraft for launch in 2016. Because Bennu is inclined about 6 degrees in its orbit relative to the orbit of the Earth, we had to spend 1 year going around the sun, come back to the Earth for a maneuver we call the Earth Gravity Assist. We flew underneath Antarctica, and we used the Earth's gravity field like a slingshot to push us up onto a rendezvous trajectory with the asteroid. We arrived in 2018. We spent all of 2019 mapping in excruciating detail the entire surface of the asteroid, and then ultimately focusing on a few key areas where we thought we had the best probability of success, selecting the site in December of 2019. 2020 was a tough year for all of us. We still had to push forward. In the darkest days of the pandemic, we were operating our spacecraft 200 million miles on the other side of the solar system, collecting that sample in October of 2020. We couldn't leave until 2021, kind of like you have to wait for a launch window to open up when the path of the asteroid passes through Cape Canaveral, Florida. You had to wait for the path of the asteroid to get back to a rendezvous trajectory. We departed in 2021, setting up a 2.5-year ballistic cruise through the solar system. We fired the engines in May of 2021, and OSIRIS-REx just flew uncontrolled for 2.5 years to that sample return in 2023, and that great moment when that parachute opened up and the capsule landed safely. Launch was one of our amazing milestones, September 8th, 2016, a beautiful day in Florida. You can see several images up there. My favorite is the one on the top right. That was taken by a colleague on an airplane as they were flying from Miami to New York. They snapped that photo and they sent it, and it's like, hey, is that your spacecraft that we saw going off into space? And we're like, yeah, sure was. Everything was fantastic. United Launch Alliance did a great job. Mighty Atlas got it right down the middle on our way to Bennu. In addition to the commemorative posters, we would always put out a series of little Valentine's Day cards. I think you can still download them on our website, asteroidmission.org. So here you can see, for Bennu, with you, it was love at first sight. And indeed, not so much, because this is when we got that surprise of that rough and rugged and rocky surface. You can see some of the early navigation camera images as we're coming on the asteroid. Quite honestly, it was a moment of panic. Another interesting thing to note here when you look at these images is it's got what I call that kind of salt and peppery texture. One of the reasons we chose Bennu as the target is because it's one of the darkest objects in the solar system, only reflecting about 4% of the sunlight that impinges upon its surface. And we inferred that that dark characteristic was due to the presence of carbon, which can make things really dark and black, like graphite. But there are these few bright flecks that you can see as the asteroid rotates in front of us, and we were really drawn to those. It's like, that's really interesting. There's some diversity on the surface of this asteroid. It is really dark. These images that you'll see are all very stretched so that you can look at the different contrast values. If you were to see this with your eyes from a spacecraft approaching the asteroid, it would barely be visible against the blackness of space. It's really like asphalt or a charcoal brick floating out there. But there's some interesting diversity, and we'll get some clues as to what that might be in the presentation. So what did we learn from the asteroid encounter? The first thing is, as we intuited from the shape, Bennu is not a solid body. It's not like a planet with a core and a mantle and a crust. It's a pile of rubble with a lot of macroporosity, meaning there's a lot of void spaces or kind of like cave networks inside of it. And how do we think that it could form such a structure? It turns out Bennu is a small fragment of a much larger asteroid. Bennu is about 500 meters across. We think its parent body, or its parent asteroid, which originated in the main asteroid belt, was probably about 100 to 200 kilometers in diameter, so many times bigger in volume. And that object was shattered when a catastrophic collision occurred about 1 billion years ago, when another asteroid collided with it at cosmic velocities, completely disrupting the original body. And then the rubble flew off in all directions, and then some of it was attracted by its own self-gravity, like liquid droplets in space. Only they're not made out of water, they're made out of boulders and gravel and dust. We flew by the asteroid, we went into orbit, allowing us to characterize its mass and gravity field to really high precision. And there we inferred a low density of about 1,190 kilograms per cubic meter. And your average rock is about 3,000 in those same units. So So that's really low density. Water ice is about 1,000, so it's only a little bit higher than ice itself. But we don't think it's made out of ice because that would not be stable in the inner solar system unless you had a protective atmosphere around it. And it would be acting like a comet with a big tail and a coma, a couple tails and a coma. And we didn't see any real cometary activity in our telescope data. So this implies that it's a rubble pile. Probably about 50% of its interior is porous, just empty space. The other thing we learned was we couldn't use that thermal data, the infrared telescope data from Spitzer or similar instruments, to say anything about the particle size. You know, we saw that it heated up and it cooled off very quickly. And on Earth and on Mars and on the Moon, when geologic materials behave in that way, it's because they have really small particle sizes. It's a phenomenon we call the thermal inertia. Inertia is resistance to change, so thermal inertia is resistance to change in temperature. If an object has a low thermal inertia, it heats up and cools off very quickly, like a sandy beach. If it has a high thermal inertia, it heats up and cools off very slowly, like a big boulder. Bennu has a relatively low thermal inertia. You can see the value there of 350 in those very complicated set of units. That's pretty similar to gravel, centimeter-sized particles. So we had predicted that it would be dominated by things maybe half a centimeter up to 5 centimeters or so. And then we saw these shots coming in from our polycam. And you can see the field of view on this is almost 70 meters across. The big black boulder that dominates this image we call the gargoyle. Official name, actually approved by the International Astronomical Union, is Gargoyle saxum, saxum being the Latin word for boulder. It's got one of those bright, kind of salty particles sitting on its wing, I would say. We call that the jewel of the gargoyle. And it's it was a real scientific puzzle. It's like, wow, we're definitely not looking at centimeter-sized particles here. That gargoyle is 15 meters tall, right? So that's the size of a building. And everything around there is at least a meter or so across. So it was a real challenge to find an area where TAGSAM would operate. We verified, though, that the thermal data was right. Bennu has a low thermal inertia, and it turned out the areas with the lowest thermal inertia, which on Earth would be the finest particles, were the biggest boulders on the asteroid. It was exactly opposite of what our scientific theory predicted. And we're like, what could that mean? It could be the boulders themselves have a low thermal inertia. They could be almost like fairy castle, kind of very loosely bound materials. There could be dust covering the boulders, or it could be a combination of those. Turns out it's probably that first one. The boulders themselves appear to be very weak and friable, so they're behaving like sand-sized particles. They're just kind of loosely packed together, maybe like a sand castle kind of structure. What about the science? Origins, right? We're thinking about how did the Earth become a habitable world? When we look at our models for planetary formation, the inner solar system was a very warm place during the early stages of planetary building. Water ice was not stable, and the Earth probably accreted without any significant amount of water on its surface or in its interior. That water had to come from the outer solar system where ices are stable. For example, when we look at some of the moons of Jupiter and Saturn and farther out, they're covered in water ice. Sometimes they have other ices like ammonia and carbon dioxide. So we think that was delivered to the inner solar system later in our history, probably within the first 500 million years of the formation of the Earth. And our hope was that Bennu may represent the kinds of objects that brought water into the early solar system billions of years ago. And one of the best early scientific results is shown here on this diagram, and I'll take a little bit of time to explain it to you. On the x-axis that runs along the bottom of the graph is the wavelength of light. And we're out between 2.2 and 3.5 microns, well beyond what humans can see with our eyes. This is into the near infrared. And then the y-axis is the signal strength. Bennu is the blue line, and it's pretty flat, which means that it's reflecting or emitting that energy at about the same intensity. And then you can see when it gets to around 2.7 micron, the signal drops significantly and then slowly returns back to the original baseline. That drop in signal is what we call a spectral absorption, and that's indicating that there's some molecule on the surface of the asteroid that's grabbing that energy and translating it into vibrational or translational energy. And we know exactly what that is because I'm showing you a couple meteorites that have fallen to the Earth, some of the rarest kinds of meteorites that we have, called the carbonaceous chondrites. And they do have that spectral feature. You can see we're comparing 3 of them. The one in green is a famous one called Murchison that fell in Australia in 1969. The red one is Orgueil. It fell in France in the 19th century. And then the orange one is an Antarctic meteorite that was collected through NASA's systematic campaign of searching Antarctic glaciers for scientific treasure from outer space. And we know this is related to water, but it's not water ice, and it's not liquid water. It's water locked up in mineral structures. And the kind of mineral that does this is called a clay mineral. And we'll see more about these when we look at the return sample. But you can see here, make new friends, but keep the old. One is silver, the other is the water-bearing clay minerals. That is our scientific gold on this mission. So we saw this data coming in as we were approaching Bennu, and I knew right then we had picked the right target. It's a wet, hydrated asteroid, high probability of having carbon compounds. And we verified that later by looking at some of the individual boulders on the surface of the asteroid. So here, again, I'm showing you some of that spectral data. We're still in the near infrared, but we've pushed out a little farther to about the 3.4 micron region. This is where carbon compounds will absorb electromagnetic energy. And these are carbon not in organic molecules, but in minerals called carbonates. You're probably familiar with these if you live in an area with hard water and you get that white crust clogging up your shower heads and building up around your faucets. Those are typically calcium carbonates because the water has some calcium in it. It's carbonated like soda water. And as the water evaporates, the carbonate minerals precipitate out. They're usually bright white compounds. And when we looked at the boulders that were giving us this signal, you can see an example there on the left, they have these white veins that are shot through them. Kind of a hint as to where the salty stuff on the surface of the asteroid might come from. And in fact, they probably are salts in the sense that the water, they were dissolved in water, that water evaporated, and the salts precipitated out. These look like veins of carbonate. This is a really exciting discovery because when we studied those meteorites, like I showed you on the previous slide, we had always thought that, there was probably ice, but it was like thin crusts on some of the mineral grains or maybe tiny snowflake-like particles. And when they melted, they only reacted within a very small region. This vein is almost a meter across and tens of centimeters thick. In order to produce something like that, you need a big hydrothermal system. Think about the mid-ocean ridge and the hydrothermal vents that we see there, scavenging calcium from kilometer scales on Bennu's parent body and depositing it over thousands to millions of years. So this was a hint that Bennu may have come from a very water-rich world with extensive hydrothermal circulation percolating through its parent asteroid, depositing these salty veins in the boulders. So when we got there, we saw that rugged surface. That was a big surprise. And we're like, okay, this isn't going exactly according to plan, but we're going to figure it out. We got a very talented team, and we're ready to be surprised. We went into orbit on New Year's Eve on 2018. There's some classic photos of the Flight Dynamics team in their tuxedos and evening gowns going into orbit to ring in the new year. 5 days later, we captured these images. And what you can see there is the limb of the asteroid, and there's a bunch of white particles that are shooting off into space. This was an eruption, essentially. Bennu turned out to be active. And at first, we panicked. We're thinking, oh my goodness, this is a hazardous situation. We decided we would monitor it for a while, and so I'm showing you some real data here. So you can see OSIRIS-REx orbiting around Bennu in kind of the aqua color there. And then all the other trajectories are particles that we observed shooting off the asteroid, and you can see the dates in the upper corner there. Bennu is constantly shooting these particles out into space. Some of them go zipping off above escape velocity and become part of the interplanetary dust population. Some of them are on suborbital trajectories. They launch up and they land back. And some of them get accelerated by solar radiation and they go into orbit for extended periods of time around the object. It's kind of like popcorn. The surface is constantly churning and throwing these things into space. And you can see the spacecraft is flying through this swarm of particles constantly. We thought these might be hazardous, and then we realized microgravity is messing with our minds. The acceleration on the surface of Bennu is 5 micro-Gs, 5 millionths of the acceleration that we experience on the surface of the Earth. It's about the same acceleration that astronauts on the International Space Station experience. So even though this animation looked like things were moving around quickly, everything actually moves pretty slowly. It's a very low energy environment. Some of these things were the size of golf balls, some of them the size of softballs, some of them the size of basketballs, but they didn't really pose any hazard to the spacecraft because of that slow motion due to the microgravity environment. And it quickly went from crisis to cool science experiment. You can see how well we did constructing the orbits of these things around the asteroid. They turned out to be great gravity field probes. So when you model a gravity field, there's what you call the degree in order. And we had committed to NASA that we would map the asteroid to 4th degree in order. And quite honestly, we were struggling to meet that. We were around degree in order 3. And then we started tracking these particles, and we were able to characterize the field to 8th degree in order, so 4 degrees higher than we had ever promised. A really cool and unprecedented science experiment. But that's not what we were there for. In fact, I had to kind of redirect the team because they all wanted to study the particles at that point, and I was like, this is great, but we're here to collect a sample. And we got to find a safe spot to collect that from. So we really need to get back to our site selection campaign. And we had 4 criteria that we needed to satisfy. The first one was called deliverability. Where can we get the spacecraft on the surface of the asteroid? The second one was safety. If we get it there, are we going to break it, or is it going to be able to get that sample home? The third one was sampleability. Is it something that TAGSAM can pick up? TAGSAM was designed to pick up things about 2 centimeters or a little under 1 inch across. And finally, is it worth it? Does it have any science value? The good news was we had the carbon, we had the clay minerals that carried the water. Those were exactly the kinds of compounds we were hoping to bring home, and they were everywhere on the asteroid, so any spot had scientific value. The challenge was going to be deliverability, safety, and then ultimately sampleability. After a thorough mapping campaign, and remember, this is all real data. This is topography from the laser altimeter overlaid with fantastic high-resolution images from the Polycam. We got down to 4 after about 50 options that we started with. And because Bennu is a mythological bird, all of the sites were named for birds that are native to Egypt. We had the nightingale, the osprey, the kingfisher, and the sandpiper site. We quickly realized sandpiper was going to be too hazardous, very low chance of getting a sample. Kingfisher looked great, high sampleability, but it was a really tiny crater. So the final 2 were the nightingale and the osprey. And they were kind of competing with each other because osprey was really safe, but the particles just looked a little too big. And nightingale looked hazardous, but it was full of relatively fine-grained material. It was also, both of them are impact craters, so you can kind of see the bowl-shaped features. They had been formed somewhat recently when another smaller asteroid crashed into Bennu's surface and excavated that material. But Nightingale looked really young. In fact, we think it might be the youngest crater on the surface of the asteroid, formed only maybe 100,000 years ago, blink of an eye in geologic time. So the engineering team was saying, we should go to Osprey. It's safe. We're going to make it to the surface. And the scientists and TAGSAM teams were saying, we need to go to Nightingale. This looks like a really fresh surface, and the particles look really small. We're going to get a lot of sample. And ultimately, the board was deadlocked. There was a site selection board, and I had to make the choice. And I took a look really at the sampleability. So here's how we kind of parameterize this. Basically, blue is good on these diagrams, and and red and yellow are bad. And so blue was where we really needed to focus our attention. And you can see over there, right, on the right, the Osprey, it has a fair bit of blue. The two circles are the probability that where the spacecraft would land, right? Everything has uncertainty to it. The engineers couldn't say exactly where they would be able to put us, but they were working hard to improve the guidance on the spacecraft after we saw that rugged terrain. And they're like, we probably get you inside that blue circle, but we'll guarantee we can get you inside the yellow one. Same thing over there on Nightingale. And I just looked at it and I said, there's so much more sample material that's at the Nightingale. We have to go there. And in the end, I made the decision, we're going to sample the Nightingale. We're going to take a little bit more risk, although quite honestly, we had pretty much retired that because we made the spacecraft really smart. You can see why they were worried. There's this big boulder hanging off the crater rim there. We called it Mount Doom because it's got that classic kind of Tolkien-esque peaked landscape to it. But look at how nice the inside of this crater looks. You can see what the average surface of Bennu looks like there. It's that rugged, bouldery terrain, but there's this little pocket of beach. I was like, that's where we got to get to. Even within that landing zone, there's some pretty big boulders. You can see the rocks inside the crater there. They're about 1 meter across. That would cause a problem for the spacecraft if it contacted it. So we had to make the spacecraft smart and autonomous. In addition to being able to update its maneuvers to kind of get in that tight little crater, which is about 20 meters across, it still had to avoid the spacecraft killing boulders. So we built a catalog of features, and the spacecraft, as it approached, it would be predicting where it was going to touch the surface. And if it predicted it was going to hit one of those boulders, then it could back away and say, you know what? It doesn't look safe. I'm making the decision. We're going to come back and try to sample another day. Ultimately, we made the right choice. You can see here some of the best images that we got, right? Nightingale was definitely a sight for sore eyes. There's the mosaic over there on the left. So in the final stages of reconnaissance, you can see Recon C, this was our third pass, we were getting 3.5 millimeters per pixel images of the surface, making sure there were particles that were about 2 centimeters across. Unprecedented resolution. And when you look at the ragged edge of the image on the left there, each one of those is a single image that we stitched together to produce that big mosaic at this incredible resolution. And it looked great for a couple reasons. First, lots of particles less than 2 centimeters. If we got tag SAM in the right spot, it was going to do really well. But there's also some of that salty stuff. You can see some of those bright particles that are sprinkled in there, and I really wanted to make sure that we were going to bring some of those home. Guaranteed to get the average dark material, but the bright stuff, hydrothermally deposited minerals, was something we were really intrigued by. So just as a reminder, this is what we thought was going to happen, right? We were going to push tag SAM down onto the surface. We were going to fire that gas. A little bit of dust was going to get kicked up. Maybe some of those centimeter-sized particles would get blown around. And we didn't just make this up. We tested tag SAM on NASA's reduced gravity aircraft. And that's exactly what it looked like. And so we were like, well, that's got to be what it is. And now let's take a look at what happened. So here we're looking at some SAMCAM images. That's the tag SAM. The gas bottles are wrapped in that black blanketing for thermal protection. And we're approaching the surface here at 10 centimeters per second. We're going to articulate the head to get it flush with the surface. That happens right there. We're coming down. It looks pretty good. Some of those boulders are a little chunky. They're maybe 10, 20 centimeters across. And you'll see when we make contact, the one that's about at the 12 o'clock position there, it's just going to shatter. Boom. And then we fire the gas. The head goes into shadow. That's telling you we're digging a hole. We're going down deep into the asteroid, and then you can see when the sunlight comes back and hits it, it kind of saturates the detector for a while. There's a lot of stuff flying around in these images here. This was actually quite astonishing. You can see an enormous amount of debris moving around as a result of the contact. It was much more dynamic than we expected. Here's another view. This is from one of the navigation cameras. It was looking off to the side, so you can see the shadow of the robotic arm coming in here. There's the tag SAM head. It's going to contact just off the field of view. And then you'll see a plume of dust right there. So we got some really fine-grained material. And then look at the size of the rocks that are being liberated by this event here. We're moving things that are on the order of tens of centimeters. This is just a giant plume of debris. You can see the shadow of the TAGSAM arm as we're starting to back away here, kind of overlaying on the dust. And now the original surface of the asteroid will appear in the upper right corner. You'll see some particles that look kind of plate-like, and they're tumbling. And lots of the area in that upper right corner is now actually being sculpted by one of the thrusters from our back-away maneuver. And then you'll see, again, as this asteroid surface comes into the field of view, there's some shadows as large particles fly across the surface. And that is an entire cloud of dust and debris that we kicked up as a result of our contact with the asteroid. There you can see the shadows across the boulder in the upper right. This was an incredibly dynamic response, unlike anything that we had seen in our laboratory testing or in our simulations. It was an amazing experiment about how a spacecraft interacts with the surface of one of these rubble pile asteroids. So, of course, we had to reconstruct the video. So I love having the old video and the new video. So this is what we think really happened. First of all, you can see the surface doesn't look smooth and beach-like. There's big, chunky rocks everywhere. And then we just sink in. There was absolutely no resistance to the downward motion of the spacecraft. It was like hitting a pool of quicksand. We fired the gas and we started to excavate a giant crater. And then the thrusters kicked in and started blowing everything that was already lofted off the surface around. And every time I watch this video, I think back to when we were making our case to NASA to select the mission, because it was a competitive selection. There was 2 other programs that we were competing against. And we said, this is going to be safe. This is going to be easy. I can only imagine if then at the site visit we said, and this is what we're planning on doing with your billion-dollar spacecraft. There's no way the mission would have ever flown, right? But that's why we explore, right? The good news is we built a tough spacecraft. Thank you, Lockheed Martin, for that. It did its job. It came away from this adventure completely unscathed. The solar arrays were folded up and away. We call that the Y-wing configuration. The active areas were far from the surface. No degradation to our power generation. You have to dump heat from your electronics through radiators. Those were working just fine. There was no indication of dust. We saw some coatings on the cameras. They got pretty dusty, and light passage was degraded as a result. But their job was done at that point, so it didn't really matter. And of course, it was a fantastic scenario for collecting the sample. We ended up going in about 50 centimeters down into the subsurface of the asteroid, meaning we got a lot of sample. In fact, we got a little too much. 2 days later, after that contact, we put TAGSAM through a photo shoot. So these are more images from the SAMCAM here, and we kind of brought the arm around and we were looking at the bottom of the head. And the first images were pretty low exposure, and I remember one of the engineers said, hey, I think I see a dust particle. And we all got up close, and then these images started coming in longer and longer exposure. And I looked over to one of my favorite people, Estelle Church. She was the system engineer at Lockheed responsible for the TAG event. And I said, I don't like this. She's like, I don't like it either. She says, what is going on? And we quickly analyzed the images, and you can kind of see inside the interior of TAGSAM, there's a dark region. There's actually what we call the troublemaker, about 3 centimeter stone, just bigger than what could fit through the TAGSAM entry chamber, was jamming open a flap that was meant to close behind after the sample was collected. So we did a great job. We probably packed TAGSAM full, which would have meant a couple kilograms of sample. But because it was propped open during the back away and as we moved the robotic arm for these photo opportunities, we were losing material constantly. In fact, you can see on the base plate of TAGSAM, there's kind of those black stripes. Those are shadows of particles that are escaping from our sample collection chamber. So we were losing material at a rapid rate. We quickly estimated, just in this one field of view, about 10 grams of sample was being lost, remembering that the requirement was 60 grams. It was heartbreaking. And I still look at this and I think every one of those particles could have been somebody's PhD thesis. And now they're interplanetary dust. But the good news was we were so successful, we were confident there was still a lot of material in TAGSAM, and we were clear to proceed with stowage. So we clicked TAGSAM into that capture ring. Notice as it goes into the final position, you'll see some more dust escapes, the last escapees before we seal it up. We severed the head from the arm, so the entire collector came back to the Earth. And then we said, goodnight, TAGSAM. We'll see you in 2.5 years. And there it is. Here comes the capsule, September 24th of 2023. After a few heart-pounding moments, that main parachute opened up. A little late, but it did its job. Thank you. Redundancy and margin saved us there. Came in for a nice, gentle contact in the Utah desert. It goes just behind this ridge, so we don't get to see it touch down, but you'll see the parachute deflate, so we know we're on the ground, safe and sound. This was an Air Force camera that took these shots coming into the Utah Test and Training Range, culminating what for me was almost a 20-year journey to Bennu and back to return this scientific treasure to the Earth. I was fortunate enough to be on one of these helicopters, so we were at the ready. As soon as the capsule entered the Utah airspace, we took flight. We saw the capsule sitting there nicely perched in the Utah desert. It's on salt flats just outside of Salt Lake City. Parachute sitting right there on the ground next to it. And here is me and my team. We're on the environmental sampling crew, so again, keeping that sample pristine is a key scientific objective. There was a chance that the capsule might have opened up, especially if that parachute didn't deploy, then we would have been dealing with a real mess, a heartbreaking mess. But it worked, and the capsule was sitting there perched perfectly on its nose cone like an Olympic gymnast that had just stuck the landing. Our job was to just, in case anything from Utah got into the sample, we wanted a record of it. So we collected soil, we collected air, we collected dust, we collected anything that might have been outgassing from the sample capsule. And I can tell you, it was like seeing an old friend, one I hadn't really seen for 7 years, a little charred and blackened from its fiery passage through the atmosphere, but in pretty good shape. Did its job. We put it on a harness on a long line and flew it back to a temporary clean room. The helicopter pilots were incredibly proud. You can see one of them is wearing an OSIRIS-REx patch on the flight suit right below the American flag there. Got it into that temporary clean room at Utah and took off the heat shield, took off the back shell, took out the batteries and the avionics, things we didn't need anymore because their job was done. In fact, you can see in the foreground there the heat shield. And then inside is the science canister, which is like the little treasure box that TAGSAM is sitting inside. We got that bagged up. The Air Force was waiting for us with a C-17 Globemaster. Very much appreciate the support of our military colleagues. Both the Army and the Air Force were an absolute pleasure to work with out there in Utah. We kind of got to know them because we spent about 3 months rehearsing all of the recovery operations at this little town in Dugway, Utah, kind of at the end of the world, and you kind of got used to it. I'm from the desert of Arizona. I love the desert, and it was a really special kind of magical place. But our time there was over. We took off on the next day, September 25th, on Monday, got it into Houston and into the specialized curation facility at the Johnson Space Center, and lifted it up. You can see it's inside a custom curation glove box, so it's constantly under nitrogen purge with no exposure to Earth's atmosphere. And there's your happy PI. Yes, we did it. We got the asteroid sample into the laboratories in Houston. Mission success. This is what it looked like. Actually pretty fascinating. So TAGSAM looks clean, and it's still nice and snug in its capture ring. But you can see a couple rings of black material, a fine grain material on the inner edge and then coarser grain material on the outer. This was really great. Here's a close-up shot of it because this meant science could start immediately. We didn't have to wait to get TAGSAM open. Some of you probably saw the media coverage about how there were some screws that were stuck and we couldn't get inside our capsule and NASA couldn't build a screwdriver to do this and that other thing. We got all that sorted out. It wasn't a big deal, but the media had a lot of fun with it, and I answered a lot of questions about it. But it didn't matter because science started right away. We scooped up this material and we got it into our laboratories, And we did get TAGSAM fully opened up in January, and material has been distributed all around the world. This is the major part of the collection here. So eventually we took everything out of the TAGSAM and distributed it into what we call these pizza trays, because TAGSAM is circular, and this had a baffle over, and we kind of just wanted to pour everything out. But in the early days, when those screws were stuck, we were able to go through the mylar flap. The one that was stuck open actually became the outdoor. We just used forceps and scoops to pull out here about 70 grams of material. And if you look in the lower right corner, you can see a 3.5 centimeter particle. That's our troublemaker. Made it home. And actually, it's a gorgeous stone. It's got about a heart shape, so kind of nice with all of our Valentine's Day themed, that the biggest piece is what I call affectionately the heart of Bennu. And I think it belongs in the Smithsonian. It's such a cool piece. I can't imagine ever wanting to break it or crack it open and study it. I don't think we need to do that. We're certainly not asking for that on the science team here. It's going to be preserved as part of the collection. And it's a really special piece. So what have we learned from the sample so far? We've been at it since September of last year. And we're really going to the origin of life. And I just want us to think about that a little bit, because the origin of life, we still don't know how this happened. And, you know, there was experiments about 70 years ago, famous Miller-Urey experiments that showed, you know, on this diagram, you can go from the bottom there, which are the molecules that are abundant in the universe, things like water, which is H2O, ammonia, nitrogen, H3, methane, carbon, H4, hydrogen sulfide, H2S, and phosphates. Those 6 elements make up about 90% of all living organisms. And they're abundant. They're the most abundant elements in the universe, with the exception of phosphorus, and it's a little more rare. Somehow you got to take those very simple molecules and make what we call prebiotic compounds. The nucleobases, which are the letters of our genetic code, the amino acids, which build up our proteins, and the lipids, which make up the membranes of our cells. And then you got to, what we call, polymerize those. You take the nucleobases, you have to add a sugar and a phosphate and make what's called a nucleic acid, and then those can form long chains like DNA, which is where our genetic material is encoded, proteins, which are chains of amino acids, and membranes, which are lipids that form spherical structures. And then somehow all of that stuff comes together and you get a cell, like a bacterium, and then it's alive. And it's astonishing to me that we don't know how this works, because we've been thinking about this as a scientific community for a long time, and it's still a profound mystery. But Bennu can help us solve some of this. So let's start with what's on the bottom there. Did something like Bennu deliver at least the basic molecules for life? Certainly, we saw that there was water, and we inferred from the spectral data that those were water-bearing clay minerals. And you can see these gorgeous electron microscope images. Note the really tiny scale bars. That's 5 microns on top there. A micron is 1/1,000,000th of a meter. And so there's 5 of those in that bar. And that's a little rosette of a clay mineral called saponite. On the bottom is a fibrous clay mineral we call serpentine. This makes up about 70 to 80% of the asteroid. On Earth, we see these minerals. They form through hydration and alteration of mantle rocks. They're influenced by temperature, pressure, and carbon-rich fluids, carbonated fluids, or soda waters. And hydrogen is an integral part of the organic molecules. About 1% by weight of Bennu is hydrogen. So definitely loaded with water. A surprise is that there's a lot of ammonia in the Bennu samples, so it's really loaded in nitrogen. Here I'm showing you a famous meteorite, that Murchison meteorite that I talked about earlier, kind of the classic meteorite for studying organic chemistry. And Bennu has 12 times the nitrogen content. So really loaded in ammonia. What about the methane? Well, we're not actually seeing methane. We're seeing more advanced hydrocarbons, what we call polycyclic aromatic hydrocarbons. And these form rings of 6 carbons. The simplest one is called benzene. And then you can see they can link up. You've got 2-ring molecules, 3-ring molecules, 4-ring molecules. And what was really interesting is that this is a spectrum, a mass spectrum. So you're looking at the different weights of the molecules and how intense the signal is, which indicates how abundant it is in the sample. And the spectrum that I'm showing on this diagram was obtained when we just took one of those dust particles, a really small one, just tens of microns across, pressed it flat, and stuck it in the vacuum chamber, and all of these were just outgassing. So Bennu has got what we call very labile organic material. It just comes right off the sample. Normally, we would sweep a laser to kind of desorb these, and we did that and got a very similar spectrum, but Bennu is loaded in hydrocarbons. We also see carbon in solid form. The two panels in the middle there are big veins of organic, kind of like tar molecules or rings around mineral aggregates. And then on the right are those carbonate minerals, the ones that we saw in those veins and in the spectral data there. Calcium carbonates, magnesium carbonates, manganese carbonates, a huge variety of different minerals. Again, consistent with our notion that Bennu has experienced extensive chemical processing, precipitating the carbonates, forming organic molecules, and lots of potential for interaction between the organics and those mineral phases. The sulfides are there. They're not as H2S, but they're locked up in mineral forms. Many of you are probably familiar with the mineral pyrite, also known as fool's gold. It's kind of a brassy-looking mineral. These are very similar to that. There's a little bit of difference in their chemistry, but they look quite similar. And they have these beautiful hexagonal crystal forms. I'm particularly prone to liking these because I wrote my PhD thesis on iron sulfide minerals, so it's really fun to see them here. But the fact that they have such a nice crystalline shape indicates that they grew in a fluid unrestricted. So there was nothing that was interfering with their growth, so they just precipitated and grew in a liquid environment. We also see sulfur in the organic molecules as well. We see iron oxides, most commonly magnetite, also known as a lodestone. This is interesting because magnetite is what's known as an organic molecule catalyst. A catalyst is a mineral that doesn't change during a chemical reaction, but it increases the rate of a chemical reaction, especially the rate of formation of amino acids, which we have found to be abundant in the sample as well. And the big surprise is, where is the phosphorus sitting? So here I'm showing you a particle. It's about 1 millimeter across. It's coated in that white, crusty material. This turns out to be magnesium sodium-rich phosphate. I had never seen this in a meteorite before, and really it doesn't occur geologically on Earth, so it's kind of a really fun scientific puzzle. Most of the time when you find phosphates in geologic samples, they're calcium phosphates. But what it looks like is happening is Bennu clearly is a fragment from a very wet early asteroid. And the calcium was grabbed up by the carbonate and formed those calcium carbonate minerals, allowing the phosphate to build up in solution. And by the time the water evaporated away, it had to bond with whatever was present, and that would be the magnesium and the sodium and maybe even some hydrogen and water. That we do have a spectrum up there in the upper right corner. This, again, tells you about the bonds and the mineral structure, clearly identified it as phosphate, and it looks like something that is called magnesium hydrogen phosphate trihydrate. I give you the chemical formula there. This is known to be a white crystalline material that's soluble in water, so again, very consistent. So I want to leave you with the idea that it looks like Bennu is a fragment from an ocean world. And when I gave a lecture at the American Geophysical Union in December, I said, hey, we just found these phosphates. Literally, it had been like a few days ago. I was presenting very hot data. And I said, if anybody has ever seen anything like this, please come and talk to me because we're really puzzled. And I got a colleague came up and he said, hey, we just published a paper last year showing that this kind of material is coming out of the plumes of Enceladus, which is one of the moons of Saturn. And this is an iconic image taken by the NASA Cassini spacecraft where you can see it's kind of like the geysers like you see at Yellowstone that are erupting out of the south pole of this icy moon, shooting ices and minerals into space, actually forming one of the rings of Saturn, the E ring. And so we have something that looks very much like this in our Bennu samples. And the graph that's over there on the left indicates that in order to get phosphate that enriched, you had to have not only water ice, but a substantial amount of carbon dioxide ice. So it really looks like Bennu maybe originated way out in the outer solar system in the region maybe around where Saturn is today. It incorporated water ice, ammonia ice, carbon dioxide ice into a big object. There was some radioactivity, those ices melted, and you had something very much like this ocean world that's currently in orbit around Saturn. A true scientific treasure. We're just beginning to understand the details of it. So look out for more science from OSIRIS-REx. And thank you for your attention.
Well, thank you very much for a wonderful talk. Unfortunately, we aren't going to have any time for a Q&A.
Oh, no.
But if you're in the audience tonight and you do have a question, please stick around. And Dr. Lauretta, I hope will answer that question for you. We do have stargazing tonight. The weather is clear, so as you leave the building, if you go across the street, you'll find our astronomy educators over there with some telescopes, and they will assist you in looking up at the stars tonight. And we do have an upcoming Exploring Space lecture coming in the next month in June, which will be about Mars sample return. So please join us for that. And as always, thank you again to our sponsor, Aerojet Rocketdyne and ULA, for their support of this series. We really appreciate it. And there's the information for the upcoming June lecture. Yeah. So thank you again very much, Dr. Lauretta. Everyone help me thank Dr. Lauretta for a wonderful talk.
Thank you.
And thank you all for joining us tonight.